All right, welcome back, everybody. We're going to take a look at section 5.3 in this lesson, assessing the fit of a line. So in 5.1, we looked at correlation coefficient, the value R, that gives us some sort of a, kind of like the strength of the linear relationship between X and Y. Then in section 5.2, we came up with the line of best fit. And now in section 5.3, we talk about a couple other things we need to look at, okay? So as it says, once we have found the equation of the least squares line, the next step is to consider how effectively the line summarizes the relationship between X and Y. Important questions to consider are, 1, is a line an appropriate way to summarize the relationship between two variables? Meaning, is really a line the best fit? Is the data linear? Or is it maybe more curved? Okay. Do the data tend to form a line, or does it tend to be more curved? Number 2, are there any unusual aspects of the data set that we need to consider before using the least squares line to make predictions? That could show up in the form of what's known as an influential observation. Or an outlier. And we'll talk a little bit about those more in a moment. And number 3, if we decide that it is reasonable to use the least squares line as a basis for prediction, how accurate can we expect predictions based on the line to be? Okay, how good of a predictor will that line be? Well, in this section, we're going to look at graphical and numerical methods that will allow us to answer these questions. Most of these methods are based on the vertical deviations, the vertical distances of the data points from the least squares lines. These vertical deviations are called residuals, and each represents the difference between the actual y value in the data and the corresponding predicted value we call y hat that would result from using the least squares line to make a prediction. So predicted values and residuals. The predicted value corresponding to the first observation in a data set is obtained by substituting that x value, we'll call it x sub 1, into the regression equation to obtain y hat 1. Where y hat 1 is a plus b x sub 1. Remember, in general, the equation of the least squared regression line, y hat equals a plus bx, where a is the y-intercept, b is the slope. So to get the corresponding y1 value, we're just subbing in the first x value to get our first predicted y value. If I wanted the second predicted y value, I would simply sub in the second x value in the data point to get that. The difference between the actual y value in the data for the first observation, y1, and the corresponding predicted value is y1 minus y hat sub 1. Okay, y1 is the actual data value. Y hat 1 is the first predicted value. Okay, and the difference between these things is called the residual, the vertical deviation of a point in the scatter plot from the least squares line. An observation falling above the line results in a positive residual, whereas a point falling below results in a negative one. This is shown in the next figure. So here we have a line of best fit. That's what this is, some line of best fit. And this represents an actual data point and another actual data point, x1, y1, x2, y2. Okay, so the actual y value here is y1. Okay, that's the actual y value where the dot is. This right here on the line of best fit is what we call y hat 1. That's what I would get if I plugged this given x value into the equation of the line of best fit. It gives me this y value. So the difference between the actual y value and the value on the line of best fit is known as the residual. Okay, and that's exactly what this is over here. Okay, here's the actual y2. Here's the predicted y hat 2. Okay, and the difference is the residual. Now, the first one would have a positive residual because y1 minus y hat 1 would be positive. This is the bigger of the two values. Over here, the second point would have a negative residual because y2 minus y hat 2 is actually going to be negative. y2 is smaller than that guy. Okay, so that's what's meant by positive and negative residuals. All right, so we compare the actual y values to the y values on the line of best fit, and we get these things called residuals. Okay, definition. The predicted values result from substituting each sample x value into the equation for the least squared line. That means that y hat 1, our first predicted value, like we saw before, we sub x sub 1 into the equation for best fit. For the second predicted value, we sub in x2. For the nth or last predicted value, we sub in our nth or last x value. So we're going to have a series of these points. Residuals. The residuals from the least squared line are the n quantities, okay, however many data points you have, that many quantities where we're subtracting actual minus predicted. And we do that for every set of y values. Each residual is the difference between an observed y value and the corresponding predicted y value once again. Okay. Plotting the residuals. A careful look at residuals can reveal many potential problems. A residual plot is a good place to start when assessing the appropriateness of the least squares line. Definition: a residual plot is a scatter plot of the x comma residual pairs. What that typically is going to look like is we'll have like an x and a y axis that'll look like this, and we're going to have the actual x values on the x axis, but on the y axis we have the residuals. Okay, and then when we look at a residual plot, and I'll show you how to do this shortly, we look at the shape of this thing. Okay, isolated points or a pattern of points in a residual plot indicates some potential problems. A desirable residual plot is one that exhibits no particular pattern, such as curvature. All right, I mean, ideally we see something like with a lot of dots kind of close to the line like that. All right, that's a residual. That's what a residual would look like that indicates a line's a pretty good fit. There's no curved pattern to that, and maybe they're not that close to the line. They can be a little more spread out, but they're kind of like all over. All right, versus suppose we look at a residual plot and the thing kind of looks like this. I mean, this has a very kind of quadratic or parabolic shape to it. That's what we call a curved pattern. All right. So in any event, a desirable residual plot is one that exhibits no particular pattern, such as curvature. Curvature in the residual plot is an indication that the relationship between x and y is not linear, and that a curve would be a better choice than a line for describing the relationship between x and y. Curvature is sometimes easier to see in a residual plot than in a scatter plot of y versus x, as illustrated in the next example. Record times. Consider the accompanying data on x equals the distance in meters and y equals the record time in seconds for men for races of various length in international track and field competitions. And this data was taken from 2016. Okay. Well, the scatter plot displayed below appears quite straight. Okay, that's what happens if we take those x values, 100, 200, up to 5,000, and plot them against those y values in the table. That's the scatter plot on the left. And yes, it does look to be fairly straight. If we were to punch these values in and come up with a correlation coefficient, I would certainly expect a value pretty close to +1 here. But while that may make one think that, yes, there's a very linear relationship between distance in meters and record time in seconds, the residual plot gives us a little bit more information. Okay, if we actually graph the line of best fit and we looked at all these vertical differences between the dots and the y value on the line of best fit, that would give us this residual plot. Okay, and what we see though is that this does have a very curved kind of shape to it from left to right. In general, a residual plot that has a parabolic shape, quadratic shape, is an indication that a line is not the best fit for the data, regardless of the R value. Even if the R value is very, very close to 1, this is a big kind of a caution. It's telling us the data fits a curve better than it does a line. And there's a lot of aspects that can go into this, and we can really think deeply about this and get into some more upper level math stuff. But at this level, that's really what the expectation for you guys to know is. If we look at a residual plot and it comes back parabolic, chances are the data is better described by a curve than it is a line. That's the end of the story. The residual plot comes back like some of the examples I showed a moment ago with dots kind of all over and no curved pattern. Usually an indication that if the R value is close to ±1, a line is a good fit. Okay. unusual points in a bivariate data set are those that fall away from most of the other points in the scatter plot in either the x direction or the y direction. An influential observation is an observation, is potentially influential if it has an x value that is far away from the rest of the data. Basically, it's like a big gap. You've got a bunch of data here around these x values, and then all of a sudden you got some x value far away. Now, if I put that dot in there, here's what the original line of best fit would look like without that last dot. If I put this dot in here, that's going to have a huge effect on the equation of the line of best fit. And that's why it's called an influential observation. To determine if the observation is influential, we assess whether removal of this observation has a large impact on the value of the slope or intercept of the least squared line. Okay? And an outlier is an observation that has a large residual. That means it's more off in the y direction. So again, if I have these points, and say this is my line of best fit, that is a pretty large residual compared to the other three. This last one is the largest of our residuals because the dot lies far away in the y direction from the line of best fit, and that's what we call an outlier. Okay, next up is this thing we call the coefficient of determination. It's the proportion of variability in y that can be attributed to an approximate linear relationship between x and y. The coefficient of determination is denoted by r squared, and that's literally our correlation coefficient r squared. And you may recall that this value is often displayed on our calculators when we run the linear regression. We get both r and r squared provided our diagnostics are on, right? The value of r squared is often converted to a percentage by multiplying by 100 and is interpreted as the percentage of variability in y that can be explained by an approximate linear relationship between x and y. Another way to think of it is basically, the way I think of this is basically more or less, an approximation to how accurate our predicted values, our predicted y hat values on the regression line will be. All right, they're going to be about 75% accurate. They're going to be about 90% accurate. Oh, they're only going to be about 24% accurate. Okay, we'll see some examples coming up. Okay, don't worry about all these terms for now. Just try to get the notes down, and then we're going to wrap this whole thing up with an example. Next up is the total sum of squares. The total sum of squares is denoted by SSTO, and it is the sum of each actual y value minus the average y value squared. Then I take the second y value, subtract the average, and square it, and I add all those up. And so here we have a little summation to represent that, the sum of all y minus average y squared. And the residual sum of squares, notated SS resid, is similar to the total sum of squares, but this is dealing with the residuals. We're taking each y value and we're subtracting the predicted y value, squaring it to come up with a positive number, and we're doing that for each pair of y values and adding them all up to, again, get this summation. Okay. The coefficient of determination, this is just a formula that can be used instead of simply squaring r or just getting it off the calculator. It can be computed by looking at 1 minus SS resid over SSTO. Fortunately, it's not something we're going to have to focus too much on here. Okay, but just know the term coefficient of determination. In a rough sense, it's basically how accurate our predicted values will be. Okay. And then we have this thing called the standard deviation about the least squares line. Recall that standard deviation about the mean that we learned about a little bit earlier in chapter 4 is basically a rough average distance each data point lies from the average value of the data. Well, this is similar to that, but it's more of a rough average distance each y value will lie from the line of best fit, above or below it. The coefficient of determination measures the variability about the least squares line relative to overall variability in y. A large value of r squared does not by itself promise that the deviations from the line are small in an absolute sense. A typical observation could deviate from the line by quite a bit, but these deviations might be small relative to overall variability in y. And here's the reminder of the formula for sample standard deviation from chapter 4. It's the square root of the sum of the squares of each x minus x bar divided by n minus 1. That was used as a measure of variability in a single sample. Roughly speaking, S is a typical amount that the sample observation deviates from the sample mean. There's a similar measure of variability that is used when a least squares line is fit. This measure of variability is the standard deviation about the least squares line. And here's the formula. It's notated as S sub E, and it's the square root of SS resid divided by n minus 2. Roughly speaking, SE is the typical amount that an observation deviates from the least squares line, above or below. Okay. And again, most of this stuff is we'll get it right off the calculator. Okay. So some ugly formulas, but let's try to put this all together with an example now, and we'll use the calculator a little bit and try to make sense of some of this. Okay. So bear with me a little bit here. If I know I sometimes hit the wrong buttons on the calculator, so be it. All right, but let's take a look at this. So I've got this example. The busiest season for Walmart is the Christmas holiday, and weekends see a tremendous number of customers. Last year, Walmart conducted a study as to the amount of waiting in time in checkout lanes its customers had to wait. On Saturdays and Sundays of its holiday season, it opened a different number of checkout lanes for customers between 1 and 4 p.m., its busiest times. The measurement was the average wait time for a customer to go through the lane and complete the transaction. A different number of lanes was opened each day. The data is below. So we see throughout the months of end of November and into December, Saturdays and Sundays, we've got, looks like the weather. So it was sunny, cloudy, sunny, rainy, whatever. We've got the number of lanes that were open, and we have the average wait time in minutes. Now, as we just kind of look at this data, I think, as you would imagine, what's going to happen is as more and more lanes become open, what's going to happen to wait time? I would expect it to go down, right? The more lanes are open, the more people that can check out at once. I would expect that to go down. When there were 5 lanes open, people waited about 12.2 minutes. When there were a lot more lanes open, that value dropped a lot, okay? So it seems to be the case here. So for question 1, it says, what is the explanatory variable? And what is the response variable? Okay, well, the explanatory is our independent variable, and that's typically our x and the thing that we're manipulating. And what's that? Well, that's the number of lanes here. So the number of lanes is like our x. And then what are we measuring based on that? Well, that's the average wait time. That's our y value. Okay. For answer number 1, make a scatter plot on your calculator and draw it below. Okay, and you guys can take a moment to do that if you'd like. I'm going to do just a very kind of crude, rough one right here. And let's see, the lowest value of x, it looks like, is 4. The highest is 12. So let's do this. 1, 2, 3, 4, 6, 7, 8. Okay, and for the y values, it looks like we got to get all the way up to about 12.2 there. So I'm going to count by 2's over here. Okay, and again, I'm just going to kind of roughly sketch this thing. So we had 5, 12, 2, 4 point, let's see, 12 comma 4.2 would be about there. 11, 4.4, 7, 6.75, 12, 3.8, 8, 5.75, 6 comma 10, 4, 10 comma 6.5, 8, 6.25, 6 comma 9.2, 4 comma 1.1, and 8 comma 5.6. About in here. Okay, so that's what the scatter plot looks like. Again, if you did it on your calculator, it probably looks a little nicer. But this leads to question 3 now. It says there is a clear outlier on your scatter plot, circle it. So again, if we were to kind of eyeball a line of best fit, for the large part, it looks like these dots are doing most of the work to create the line. And we've got this one guy that's really far away in the y direction. There's our outlier. Okay, that would be our outlier. Give a reason that would justify eliminating the outlier here. Well, that takes a little more thought and it's actually why they gave us the weather here, okay? Notice this point showed up here, and if you look at the weather, what do you notice? It's the only day in this whole survey that did what? Snowed. So while there were only a small number of lanes open, because it was snowing out, it seems reasonable to think that maybe there wasn't as much business as usual. And so therefore, it only took an average wait time of 1.1 minute to get through checkout, even though there were only 4 lanes open. Okay? So I would say in a situation like this, the weather is certainly a good reason to eliminate the outlier. Now, generate the least squares regression line that describes the data with the outlier eliminated. So basically what we're going to do is we're going to plug in X values into list 1, Y values into list 2, but we are most certainly going to ignore this. It says ignore the outlier here, okay? And you will never have to do this on your own, and you will be told whether or not to ignore an outlier, okay? I don't want you to think that, oh, other problems, I got to think about this. No, this is just specific to this example, okay? But let me bring up a calculator. It's actually a TI-84. It's just what I have to work with here, but the functionality is very similar to what we're used to, okay? All right. So if I go into stat edit, I've already taken some time to put all the data for X in list 1 and all the data into the list for X2, and I did get rid of this, okay? That's not in there. In fact, you can see 6, 9.2 right here, and then it goes to 8, 5.6 right there, okay? So again, now if I want, I can do stat, calc, and I can do number 4, my linear regression. Okay, X list is list 1, Y list is list 2, and we can go down, keep hitting enter until we get down to calculate. Okay, and we should get this information. So we have the line of best fit, and it also gives us the value of R and R squared. Now, if yours again isn't showing, you got to go second to 0, and you got to scroll all the way down into the D's. This is alphabetical. This is again just a quick reminder how to turn your diagnostics on, or you won't see that R stuff. So eventually we'll get there. There we go, diagnostics on. Make sure those are on. And then if you were to now run your linear regression, you will get those values. Okay, so I just want to make sure you remember how to do those. All right, and so number 5, generate the least squared regression line. Rounding to 2 decimal places. So we would write this as y hat equals, now the value of the slope is a here. They have it in this form, ax plus b. So next to x is our slope. So I'm going to write negative 0.96x and plus b plus 14.96. And there is the equation of the least squared regression line here, okay? And I've written that in. You can see that right here. Give the meaning of the slope. Well, it's a negative slope. And what does that mean? Well, it means for every increase in x by 1 unit, what do we expect the y value to do? Well, we expect the y value to go down by about 0.96 units. So roughly speaking, what is the meaning? Well, x represents what? The number of lanes that are open. So for each new x, for each new lane that opens up, the y value, the wait time, goes down by 0.96 seconds on average. Okay? For each new lane that opens, wait time goes down on average by 0.96 seconds. And that's what the value of the slope means here. What specific point is the least squared regression line always guaranteed to go through? Well, again, that's the average x value, average y value that we talked about in the last lesson. And you could compute those values here if you really wanted to. But in general, it always goes through average x, average y. Describe the data in terms of form, direction of strength. Well, look, when we get rid of that outlier, the data tends to go down and to the right. As the number of lanes opens up, the wait time tends to go down. Now, basically, I'm going to kind of answer 8 and 9 the same way here. Let's look at what that R value was. R is about negative 0.88, we'll call that. Okay. R is about negative 0.88. That is a strong negative linear correlation. Okay. And that's basically the same as the answer to number 8. Okay. The strength, it's strong. It's between that 0.8 and that 1, that negative 0.8 and negative 1 that we saw on the number line for R. The direction is negative. It's going down and to the right. Okay. And there we go. Strong negative linear correlation. That would be answers for both 8 and 9. Find the value of R squared. Well, that's right here as well. R squared is about 0.78. If I take negative 0.88 and squared, I get about 0.78. Okay. Well, as a percentage, that would be 78%. So the interpretation is, we can attribute about 78% of the variation in Y to the linear variation in X. That's the technical way to say it. Or you can say interpolated values, right? Those are our predicted values between the lowest and highest X in the data. Interpolated values are about 78% accurate. All right, and that's what R squared is. What is the predicted average wait time if Walmart opens 9 lanes or if they open 7 lanes? Well, here's just where we can practice using the equation of the line of best fit. So basically, what's the predicted average if we open 9 lanes? Well, I would say y hat's going to be negative 0.96, and the number of lanes is given by our x value. And if I want for 7 lanes, same idea. Y hat will be negative 0.96 times 7 plus 14.96. Again, doing that on the calculator pretty quickly. Let's see what we get. Negative 0.96 times 9 plus 14.96. We would expect the wait time to be about, whoops, I missed a decimal there. Bring this back up and insert a decimal at the beginning. There we go. There we go. And that seems kind of reasonable, okay? So look, so for 9 minutes, we would expect about a wait time of 9.32 minutes, 6.32 minutes, sorry, transposing my numbers here. And then I'm going to go second enter, and that'll just bring up the same thing I just punched in, and I can just curse over to the 9 and change it to a 7. That's probably the quickest way to do this, as long as I can get the right spot. There we go. And 8.24 minutes. And that makes sense. The more lanes, the less time. The fewer lanes, the more time to wait. And if we look at our graph, let's see. At 9, we would be right about here, which seems to be a little above 6. That makes sense. And with 7 lanes open, I would be a little higher, somewhere up above 8. And so that answer makes sense. What is the difference between the actual waiting time and the predicted waiting time for 7 lanes? So this is actually asking us to compute a residual value. Okay, it just wants one specific residual value. So basically, I want the actual Y value for that go with 7 lanes being open, and I want to subtract the predicted value. What's the actual value? Well, let's look at the data. Do we have any data where 7 lanes were open? Yes, we do. Okay, so if you look up there, the only Y value that goes with that is 6.75. So that's our actual Y value. 6.75 minus the predicted value, and that's what we just came up with in part 12, okay, in question 12. That's the 8.24. And so if I look at that difference, okay, 6.75 minus the 8.24, which is the value we got off the line of best fit, we have a residual of negative 1.49. So that means the actual Y value was almost 1.5 values below the predicted value. Okay. If Walmart decides that it's, let me write this in, negative 1.49. If Walmart decides that it wants its customers to wait no longer than 4.5 minutes, how many lanes should it open? So now they're giving us the Y value. The Y value is the number of minutes. So again, I'm going to use this line of best fit equation, but now they want to know the number of lanes. I'm going to solve for X. So I'm going to actually sub in 4.5 for Y, and I'll solve for X. I'll just do the work here. Negative 0.96x plus 14.96. And now we just do a little bit of algebra to solve for x. So we're going to subtract the 14.96. Let's see here. Come on. And we're going to get negative 10.46. And now I'm going to divide by negative 0.96. And so what do we get? Divided by negative 0.96 is about 10.89 or 11 lanes. Okay, so if we don't want people to have to wait more than 4.5 minutes, we should probably open 11 lanes. 10's not going to quite get the job done. If Walmart wants its customers to wait no more than 10 minutes, how many lanes should it open? So kind of the same idea, but now I'm going to plug 10 in over here for Y. 14.96. So let's subtract. We're going to get negative 4.96, negative 0.96x, and let's divide again and see what we get. So negative 4.96 divided by negative 0.96. And we're going to get about 5.16, okay? So realistically, we would need to open up that 6th lane. What is the predicted average wait time if Walmart opens only one lane? So again, I could come up here and now plug 1 in for X. And that's just going to end up being negative 0.96 plus 14.96. That's going to be 14 on the nose. So if we were only open one lane, we would expect a 14-minute average. What is the predicted average wait time if we open 20 lanes? Well, let's see what we get if we actually plug 20 into this equation. So negative 0.96 times 20 plus 14.96. And we get negative 4.24. Why do the last two problems and answers make little sense for the problem? Okay. Well, for one, Walmart's not going to open just one lane and have everybody waiting. So that's not realistic. And notice, one lane was never a value for our X values. That would be an extrapolated value. We're looking at X values from a low of 4 to a high of 12. So we want to avoid X values using predicted X values for interpolation purposes, okay? So we wouldn't do that. And plus, Walmart wouldn't open one lane, and a lot of angry customers would be there. What is the predicted average wait time if they were open 20 lanes? Well, that doesn't make sense because you can't have a negative wait time. You can't wait less than 0 seconds, right? That doesn't even make sense. So again, you know, what these questions get at is kind of avoid extrapolation. Don't use the line of best fit to predict Y values for X values that are not between the lowest and highest X values. Okay, so avoid extrapolation. In a real world sense, these don't really make a lot of sense. All right. Create the residual plot for the bivariate data. Based on the shape, is a line a good fit for the data? And what is the standard error about the least squares line? Again, this can all be done on the calculator. So let me attempt to show you how to do that. Okay. So what we're going to do is if you actually go second list, number 7 rather, there's a residual feature. I don't think this will come up unless you have data entered into lists 1 and 2 and you run that linear regression analysis. This will now show up. So this is in here, okay? So what I want to do is I actually want to store these residual values into list 3, okay? So how do we do that? If I get out of this, all right, we're going to go go back in list number 7 for resid, And now over here, there's a store button. So I'm going to hit store this in list 3. So I'm going to hit second L3, and I'm going to hit enter. And you just kind of get this, whatever. But now if we go into our stat and we go to edit, you're now going to see in list 3 our residual values, okay? First residual value a little bigger than 2. That means that the actual Y value at 12.2 is going to be about 2 steps above where it will be on the line of best fit. All right. Here's a negative one. The actual Y value of 675 is about 1.473 below where it would hit the line of best fit. So these are the actual residuals. Get them right on the calculator here. And now what we can do is we can actually look at the residual plot. What we can do now is plot L1 against L3. The thing is that Zoom stat does not work for this. What we're actually going to have to do is set up our window. So to do this, we have to look at L3, and we're going to find the lowest and highest values, because this is what's going to be plotted on the y-axis. And we're going to look at L1 and do the same thing. So the low value for L1 was 4. You can go back to the list, but that was the lowest. And the high was 12. For list 3, the low value seems to be this negative 0.166 is what it looks like to me. And the high value seems to be that 2.05 and change. Okay, so here's what we're going to do. We're going to go second. Let's go window first. All right, just window. And X, we said, went from like 4 to 12. I'm going to just start at 0. That's fine. And this goes a little higher, but I'll go just to 12. The scale is what the tick marks are. We can count by ones. For Y, now look, the lowest Y value was this. So I put the Y min at -2, just a little below this. The high is 2.05, so I'll go a value just a little above that, call it 3. And again, I'll count by ones, and don't worry about the resolution or the delta X. Don't worry about any of that stuff, okay? So now that's set up. Now what we're going to do is we're going to go second, stat plot, enter, turn that on, make sure you've got the scatter plot, and now make sure it's list 1 against list 3. Okay, usually it'll be list 2 in there. Now just hit the graph button, and this is our residual plot. Here's the residual axis that goes up 1, 2, 3, -1, -2. Here's our X values, 1, 2, 3, and our first one was at 4. And now we see these residuals. This is not what I would call a parabolic shape. To me, these are dots kind of all over the place. When I say parabolic, I mean a very clear left to right kind of parabola. That's not what's going on here. This is coming down, up, down, up. This is very zigzaggy. This is an indication that a line is a good fit. So here's the residual plot. You could then put this over here if you wanted to, but again, it can be done right on the calculator like I showed you. Based on the residual plot, is a line a good fit? Yes. The residual plot, the residual plot is not parabolic in shape. That's the extent to your responsibility now. If it's parabolic, the answer is no, it's not a good fit. If it's not parabolic, the answer is yes, a line is a good fit. And now, what is the standard error about the least squares line? Well, that's, again, on average, how far each residual lies from the line of best fit. And we can actually do this on the calculator pretty easily as well. If we go into stat calc and we do our one variable stats, that gives us average and standard deviation. We just want the standard deviation for the residuals. So we're going to make sure we tell that then to take list 3. Okay, the residuals were in list 3. I am trying my best to get that. Second, L3. There we go. And calculate. Okay, and it's the sample one that we're after right here. So about 1.27 would be our standard error about the least squared line, about 1.27. On average, a Y value is either 1.27 above or below the Y value on the line of best fit that it is associated with. All right, folks, and this pretty much wraps up the bivariate data analysis. Do your best to study this stuff and ask your questions, and I will talk to you guys soon.